The name of this video is Volume Magnetization Current a JM Vector Part 2. In Part 1, we outline the model, the physical model we intend to use now in Part 2 in order to find an important relationship for Jm, which is similar, if you want, as what we did in the case of the electric materials for P. And eventually we're going to find one for JMS, which is J on a surface similar to sigma P. All right, so how do we proceed in this case? Well, so remind you that in the previous video, in part 1, we consider the skin hat kind of structure where we have a border gamma. So our border gamma, which is associated with an infinite set of possible open surfaces, capital sigma gamma, which have gamma as a border. And I want to consider this structure within an object, like a magnetic material. And there, I want to see how many little loops of current associated with atoms, like in the atoms, there is a proton and the electrons moving around. So how many of these current loops of currents, very small loops of currents, is actually linked with this line gamma. So that's the aim of the problem here. So in order to understand this, let's only take a small segment of length dl, as I already briefly mentioned in the previous video, of this line gamma. And so this will be on a straight line, so it's a dl. The line gamma is a generic curve, but when it's so small, I can basically just linearize it. And so it looks something like this. So this will be our line gamma. And of this, I'm just considering a segment of length dl vector. Let's say from this point here to this point here. This is our vector dl. And again, it belongs, this dl is in the neighborhood of a point capital P or capital Q on the line gamma, which we considered in the previous video. All right, so now that we know that in general, each atom with the protons and the electrons moving around effectively forms a little loop of current. So all these loop of currents are completely randomly distributed because of the Maxwell-Boltzmann distribution of the temperature capital T of 300 Kelvin, let's say, at room temperature, inside this object. So all these loops will have some whatever random orientation. So in order to give a statistical meaning to this ensemble of loops which are randomly oriented, what we did in the model in the previous video, we chosen a direction which we call normal as a reference direction and projected all the areas. Each area is the same, but they are oriented in different ways, and we projected them on this normal reference direction. And so by means of that, we were able to find a mean area for each of these loops, normal area, which we just called A, and a mean direction N. So let's say now that we consider one of such loops. So we have one of such loops, the average one, which will have a certain average direction. So this average direction, if you're lucky, could coincide with the direction of the L, but it doesn't have to be like that. It can be more generic. And so the more generic case is that the direction N of my loop of current associated, the mean, the average loop of current associated with the atoms, with the Avogadro number of atoms, is oriented in a different direction, forms an angle theta with the L. And so let us say, for example, that each of these loops, the mean loop with respect to dl, is something like this. So I consider one which is centered exactly here, for simplicity, at this point on gamma. So let's slant it well so that it makes it's nice to see what's going on. So this one, let's say, it will be something like this. This is the axis of this loop of current. I'm trying to do a semi-3D representation of this problem. Okay, so something like this. And so now here we want to consider a loop of current which in 3D will look something like that. Okay, so this is one possible loop occurrence, which now there is an Avogadro number of them, so there would be one located more or less at this location, this point where DL begins. Now, this specific loop occurrence is characterized by a direction n, normal here. This direction n, in general, forms an angle theta with the direction of dl. Again, if you're lucky and the average of all these loops occurrence happens to have the same direction of dl, then that's a lucky scenario. But let's consider a more generic scenario where they make an angle. So again, this is the average, and so let me remind you what this means. This means that the area of this loop is what we call A, and A, I remind you, actually has to be intended as the mean value of A perpendicular, see part 1. In addition to that, the N has to be intended as the mean of all possible N's. We remove this symbol of mean just to simplify the notation a little bit. And of course, the current I, since the material is homogeneous, let's say that it goes in this direction, the current I is the same for all these loops. This is the current I associated with one of these loops occurrence, of course. And it's the same for all loops, for the Avogadro number of loops in the neighborhood of in this region of space inside my material. Now, let me sketch here a cylinder, a slanted cylinder, which has this loop occurrence, this average loop occurrence as the base, and there will be another base here. So let me sketch it in the following fashion. Okay, so this one is our slanted cylinder. Great, so this one is another loop of current. So let's show only this region, this one we dash it on the back side. Great, so this is our other base down here, okay? So this is our slanted cylinder. This concept is the same as what we have done for the electric materials. We also there, in order to find rho p, we consider a slanted cylinder. So the slanted cylinder always is the most general case because it takes into account for any direction here n, which is not parallel to this dl in this case specifically. All right, so now if I look at this construction, what kind of loops? This is a loop of current. This is my line gamma. So you need to remember that this is a closed line gamma, and I want to see how many loops of currents are linked with this line gamma. Locally, infinitesimally, if this eventually is going to be our little volume, because it's going to be infinitesimal since the length is dl, what kind of loops will be linked with gamma? So of course, this one is linked because I have this loop and this gamma goes through it. So in order to go outside gamma, I need to cut gamma. So it's obviously linked. And see all the definitions of linkage we have done in Phys 242. So what about, for example, a loop? So let me do another line here parallel to this. So let's say this line here. These lines are parallel. So let's consider now a point which has a center, let's say, somewhere here. So now the center of the loop, let's say that is here. Or in this case, which is in the middle of this cylinder somehow, this part of the cylinder, well, this loop clearly will be also, we need to go all the way here, so it's going to be this length from here, start from here, and we end up somewhere here. look something like this. Okay. So this loop of current, which is centered somewhere here, in this point inside the cylinder, is this loop of current linked with the cylinder? Yes or no? You should stop for a second, think about it. Now, if you came back, clearly it is linked, because still, as you can see, in order to remove it outside, I need to cut the line gamma. So this is also linked. Which one is the last loop, where it has to be the center of a loop in order to be the last possible center, in order to be still linked? Obviously, it has to be somewhere on the edge here of the cylinder. So this is the last center of a possible loop that is still linked to the cylinder. It's the last one. Well, actually, you need to be a little bit below, okay, there. So in fact, if this is our line here, so let me sketch it again. Is like this. So in this case, the loop will look like this. Okay, this loop, which I'm dotting here, will be the last one to be linked because it barely makes it to touch gamma here. Okay, as soon as I take a loop which has the center somewhere outside, let's say here, well then this loop clearly will not be linked anymore. Why is that? Because we have this length, which is like this, so this loop is going to look something like this. So this kind of loop where the center resides outside the volume of this length cylinder is not going to be linked anymore. So this is the last one which barely makes it to be linked because it touches gamma. This one doesn't touch gamma. And so obviously this is like I have the line, the loop is here, and so I don't need to break anything to disjoin them. Great. So now we understand qualitatively what kind of loops, okay, of average loops actually is linked with gamma and which kind of loop is not linked. In the non-trivial case, which is that where n, the normal direction of each loop, which is the average one, it's not the same as the L. Of course, if it was the same, this slanted cylinder would become a simple trivial cylinder. So it would become, in the trivial case would be something like this. Which happens to be obviously a subcase of the one we are considering. So we're not going to consider this trivial case. You can do it as an exercise, but it's obviously just a subcase of the one we are considering here. Great. So now that we know that, what is by definition, what is the current DIM, the infinitesimal current, DIM, magnetization current intensity, DI because it's associated with the DL. Okay, which is linked with this DL segment of gamma. Eventually, you want to find the linkage with the whole gamma, which is a closed loop, of course. But only if I look at the infinitesimal part, well, it has to be, in general, is the flux of a JM, which we intend to study, the NDA. Okay? But how can we qualitatively, intuitively now, write down, looking at this picture, this DIM? Well, obviously, we have loops. What are the loops, in other words, the linked with this DL? Well, the current of each loop is I, so we need to have I, the current intensity is I. How many loops I have? I have capital NL loops, which is approximately an Avogadro number. Since we are looking at this locally, I need to find the density, so I need to use the density capital NL divided by V, which dV, which we've seen before, well, V. And so this is small nl, which is the density of loops per unit volume, okay? Small nl is the density of loops per unit volume. We defined this in the last video. Okay, so this is the current of each loop times the number of loops per unit volume. If I multiply this times the volume of this slanted cylinder dV, I should obtain the current DIM, which is algebraically linked with this infinitesimal element, segment of element of length dl, which is part of gamma. And then to obtain the linkage with all the entire gamma, I simply need to integrate over the line gamma. Okay, so it's I NL dV. I is the same for each loop, this I here. So how many are linked? Of course, I need to multiply times NL, which is the number of loops per unit volume. And those which are linked are those which are contained within the volume of this slanted cylinder. If they are not contained in this volume, like this one which is outside, they are not linked. So clearly this dV is the volume of this slanted cylinder. And so how do we find the volume of this slanted cylinder? We assigned this already before. So dV, which is the volume of this cylinder, clearly is the base A times the orientation n dotted with the L, which eventually gives us a cosine of theta, which makes sense because it's the height of this slanted cylinder. We have seen this before when we studied the electric materials. So now we know what is this volume dV. This implies that we can rewrite eventually here dim as I, the current, times NL times A times N dot dL. But now if you look at this, do we remember what is this quantity here? And what is the quantity IAN? So if you don't remember, stop, pause for a minute and think about it, then come back. Okay, now if you came back, this is nothing but the mean dipole moment, magnetic dipole moment associated with all these loops in the model we have chosen to use. Which means we can rewrite this as NL, the number of loops per unit volume, so the density of loops, times the mean value of the magnetic dipole moment M, which is given by this quantity, mean value because A and N have to be intended as mean value. So here I keep it just to remind ourselves that it's a mean value. So NL we have it, and this has to be dotted with dL. Now, if you look back a few videos ago, you should know what is NL times M. So if you don't remember, pause for a minute and come back. So NL, the number of loops per unit volume, times the mean value of the magnetic dipole moment is given by, okay, if you came back, you should remember that this is capital M, the magnetization vector. Remember that we defined this as the limit for delta V, which goes to 0 plus of delta M over delta V, and that's actually exactly what we find out. So this is our M, which means DIM, so this we've done in a previous video, very similar to what we did back in the case of the electric materials, where we had P. Okay, it's very similar, the concept. So here now we can rewrite DIM as finally capital M locally dot dl. Now locally, because this is obviously true in the neighborhood of any point here, of this point here, in the neighborhood of this point there. So what if we want to extend it to the entire gamma? Because I remind you that eventually this gamma, it was like this. So this is a line gamma. And I just took a little part of length dl here, which is this part here, starting at this point, which is this point. Let's call this point capital P. So this point here is capital P, okay? This area is what we call capital sigma gamma, and there is an infinite set of them. Okay, so now if we know that, clearly in order to get the entire number, the complete number of loops which are algebraically linked with gamma, and therefore the total current IM, we need to integrate. And so the way it works is that we want to integrate over the entire closed line gamma DIM. This has to be equal to, from this equation here, the circulation, if you want, of M, the magnetization vector, dot dl, or dot TDL, if you want to call it like that. And this has to be equal to what? To Jm dot NDA, the definition of, under stationary conditions, and we know this I is stationary. So since I is stationary, is steady, the steady or stationary current, DC current, well then, this is the definition of current intensity from the current density, is the flux of the current density. And so since it's the flux of the current density, is the flux through the open surface, capital sigma gamma, in fact, any capital sigma gamma, not only this one, any, could be also this one, which has gamma as a border, of Jm dot NDA, so it's the flux of Jm. Now, as always, when you see an equation like this, you want to use Stokes' theorem. TH for theorem. So by means of Stokes' theorem, what we obtain is that we can rewrite this line integral as a surface integral. So we're going to get the surface integral on the open surface capital sigma gamma of the curl of m dot nda, which has to be equal to the surface integral on capital sigma gamma of Jm dot nda. How does it look this in local form? Well, we know that due to the arbitrariness of sigma gamma, which is also a fixed surface in space, since it's arbitrary, as always, we can simply equate the arguments of these integrals to the integrand functions, as always. This is the usual proof we have done many times. And so we obtain that the curl, the Jm, let's invert it, Jm from here, has to be equal to the curl of m. So the curl of the magnetization vector has to be equal to the magnetization volume current density Jm. Okay? So let's circle this one because it's the main result of this video. Okay. So let's recap this video. So what are we trying to do here? In video part 1, we introduce a model. We know that we have a region of space, a given magnetic material, homogeneous, that this is made from the same atoms. Each atom is a proton with electrons moving around, forming therefore loops of currents. All these loops of currents are arbitrarily oriented, randomly. Why is that? Because they are in a Maxwell-Boltzmann distribution because of temperature at the beginning of the experiment. They're all randomly oriented. So I have many, an Avogadro number of loops randomly oriented. I consider line gamma and one of the possible infinite sets of open lines as surfaces, capital sigma gamma, associated with that border. And so what I want to find all possible loops which are linked, this is not linked, which are linked with this line gamma. So I start from an infinitesimal piece of this line gamma, and I try to look at these loops. First of all, we need to make a model, because these loops are random. So they're all randomly oriented. They have the same areas, but they are randomly oriented, okay? So remember that I define a reference direction, which I call normal. If I choose this as a reference direction, I project all these areas, therefore obtaining I normals, which I average out. The directions I also average out. So effectively, I end up finding one given certain loop, which is the reference loop. It looks like this, with a certain direction n here, which is exactly the one I have here. So this is my representative average loop. So a point capital P, which is this point here at the beginning of the L, this loop would look like this. So it forms an angle n in general with the L. It could be aligned, but in general it's not. This loop is clearly linked because it crosses, the area of this loop crosses in a point gamma. So now I can define this length cylinder, which allows me to visualize what are the loops which are actually linked. The last kind of loop which is linked is the one, the center of which is at the border of this, on the other surface of this loop, of this cylinder. Any loop which has the center outside this, the surface of the cylinder, of course, is not linked anymore. Like those ones, they are not linked, okay? So now that I know that, clearly the current Im has to be the current of one of these loops, which is the same in static conditions, times the number of loops per unit volumes times the volume. This makes totally sense. This is my current, infinitesimal current associated with dV. dV is the volume of a slanted cylinder, which is Am dot dl. We have seen this before. So the Im, I just need to do to substitute this volume in here, and I obtain that it's nothing but m, by definition, we've seen in the previous video, dot dl. In order to find, instead of dim, Im, I need to integrate over the entire line, and so, which is the circulation, since it's a closed line of m dot dl, because of this relationship here. This is nothing but static conditions, the flux of Jm, which is what I want to find. So this Jm is the unknown, is what I'm trying to find, a law for this Jm, which eventually is this law down here. So I do that, I apply Stokes' theorem, and I obtain that, of course, the Jm, which is what I wanted to find, is the curl of m. So I know that this one always creates lots of problems. I hope now, with all these visualizations, we are able to understand what I mean by means of all these integrals and by means of this model of the loops which are somehow linked with this line gamma. And that's it.